from our ICT projects, and the first presentation is going to be done by Jose Rivera Perez. His presentation title is The Effect of IFIT Specimen Geometry and Test Configuration on the Fracture Process Zone for Asphalt Materials. I think many of you know who Jose is. He's a PhD student in our program here. Tell us something that we don't know, Jose, about yourself. Like, for example, how many number of likes you get with the picture, for your picture with Chancellor?
Overall, I should get 100, 150, like depending on the hour of the day when I post it.
This is every hour?
It depends on the time. We can have a whole session about when to post on Instagram and in Facebook. You need to go into the rush hours.
Well, in the meantime, while he's presenting, you can go ahead and check how his picture is doing with the Chancellor. But let's go ahead and get started with the first presentation, and I will introduce the second presentation when Jose is over.
So good afternoon, everyone. My name is Jose Rivera. I'm from Dr. Imar Alcari Research Group, and today we are going to be talking about the effect of the IFIT, of the Illinois Flexibility Index test, specimen geometry, and test configuration on the fracture process zone of asphalt materials. So here in the ICT, 4 years ago, we developed the Illinois Flexibility Index test to evaluate the cracking performance of asphalt mixtures. Basically, this test consists of a semicircular sample that is tested in the 3-point bending configuration, similar to other fracture tests that are in the literature. And the specimen is, we typically cut these specimens from the super paved gyratory field with a 50 millimeters notch thickness and 150 millimeters diameter and a 15 millimeters notch length. This sample, during the test, we measured the load and the displacement of the load and the displacement applied to the top of the sample, and we obtained the load versus displacement curve. The load versus displacement curve indicates us two main parameters. The first one is the fracture energy, that is basically the area on the load versus displacement curve divided by the physical ligament area where the crack is propagating in the specimen. The other parameter that was introduced with the incorporation of the IFIT is the slope at the inflection point. This slope is a parameter that indicates us how fast this crack is propagating during the testing. A steeper or a higher value of the slope will indicate us that the crack is propagating fast, and this is an indication of a more brittle mix. A less steep slope, a more shallow slope, lower value of the slope will indicate us that the crack is propagating slower. The flexibility index that was introduced with the IFIT is basically just dividing the fracture energy by the pulse peak slope. And this parameter at the Fi increases. What does that mean? That I have higher energy, so the material has higher capacity to prevent the crack initiation and the propagation of the crack. And also, because the slope is in the denominator, we have a higher value, we will have a less steep slope, a lower value of the slope. So will indicate that the mix is more flexible and can handle more cracking in the field. The IFIT is as many cracking tests has some limitations. One of them is that the IFIT is susceptible to the specimen configuration and the test parameters. We saw from the literature and from a previous study that I worked here in ICT that the thickness, the notch length, the air voice, and the loading rate are the main parameters that if you play with them and if you change them from the typical specification requirements, you can get misleading IFIT values. And we have reported this in the literature. In this study, we wanted to look a little bit further of the possible reasons that why this is happening. And that's why we decided to look at the fracture process zone to try to help us to explain us why the thickness, the notch length, the air voice, or the loading rate is affecting the IFIT values. So before that, I want to define what is actually the fracture process zone. In cracking tests, typically in fracture mechanics, the fracture process zone is defined. Here is a sample description of an image of the SCV test. And the fracture process zone is typically when you are doing the testing, before you see a microcrack expanding, you will see that close to the notch tip, you will have a region where microcracks are forming. And those microcracks are inducing strains and deformation in the material close to the notch tip. And basically, during the test, before the peak load, you have the development of this region with this microcrack, and this microcrack eventually would cause that the microcrack propagates in the area where the microcrack developed originally. So basically, the fracture processing area controls where the crack is initiated, and the path where this crack is may control the path where the microcrack will propagate and the failure will occur. So microcrack is not something that we can see with the naked eye. We need some measuring techniques to able to detect it and measure it. In this study, we use digital image correlation, that is an image technique, to detect where this cracking is occurring. Digital image correlation typically just consists of a camera, high resolution camera, that is taking pictures of the specimen during the test. The pictures are taken during the test when I'm failing the eye-fit specimen, when I'm performing the test, and we take one image before the test. All the pictures taken during the test are compared to that image before the test as our reference image, so we can able to detect how each subset, that is just a small collection of pixels, basically just look at it as pixels, how each pixel move during the testing. And that's what you see here in the image that I showed here. We can see the full field of the image that we took. We can see how each pixel is moving and how each point of the material is deforming during the test. And this technique allows us to do the testing at intermediate temperatures and low temperature at any moment. Basically, when we apply this technique to the eye fit, we can see the image that we see in the screen. We can measure how the fracture process and how those strains are developing before that microcrack propagates. Here you can see 5 images that I selected of one specimen that I tested before the material fails. At image 17, nothing happened. I haven't started the test yet. And in image 21, we are at the peak load of the eye-fit specimen, so we have the full development of the fracture processing. You can see in the intermediate image how the fracture processing is developing. When you see the fracture processing is asphalt is a composite material, so you will see that the fracture processing will develop in the matrix surrounding the aggregates where you have the binder that is the most compliant component of the asphalt concrete. We use fracture processing in many occasions in previous studies. One of them was the use of fracture processing to detect how the recycled materials are affecting the behavior of the mix itself. In this study that I'm just showing here a snapshot, we tested several mixes where we increased the recycled content. In this figure, the first column indicates that the material has no recycled material, 0% recycled asphalt shingles, and the other two images has recycled materials, has shingles in it. And in the case of the dose, we are testing at -12 and 25C, the same testing. We were able to see that as you increase the recycled material content, you make the mix stiffer. And also, if you decrease the temperature, of course, because of the behavior of asphalt itself, the material will also stiffer. And that translates into the fracture processing, and you will see that stiffer material will have a smaller fracture processing, and a fracture processing that is concentrated close to the notch tip. So it's indicated a more brittle mix. And the opposite when I increase the temperature or decrease the amount of recycled material. So we apply similar behavior, similar reasoning into this study to evaluate the effect of the specimen configuration. Before that, in this study, to try to simplify the image that we are showing, I'm creating this fracture processing mapping that is just the picture that I show you and just plotting in that all the region where the fracture processing developed. So what is the fracture processing in this study considered as? We consider all the strains higher than 3,000 microstrains as part of a fracture processing. This threshold came from previous studies and from evaluation that we did, and just to keep one constant value for all the testing that we did, to have an indication to be comparable with other mixes. In this study, we selected one asphalt mix, one control mix, virgin mix, no recycled material, and we prepared the sample based on as I mentioned before, of the superplate gyratory peel. the mix has 6% binder content and 15.2 DMA and N90 design gyrations. So to do the testing matrix, we basically took the same mix and we did iFit specimen that we just changed either the thickness or the air voice or the notch length or the loading date. For example, in the case of the thickness, we changed the thickness and all the parameters were kept according to the standard of the iFit. And the same thing with the air voice and the other parameter, the notch length. So basically, we are just doing a parametric study. We're using one of the parameters for each of the evaluation that we are done here. So let's go over each of the parameters that we evaluate so far. The first one is the thickness, how the thickness affected the iFit results. I want to just clarify that in this case, we have the same mix. So all the things that we are seeing are not related to the mix. These are specimen and configuration effect. The first thing is the thickness. We saw that when I increase the thickness, the flexibility index decreases. And this decrease was because we have the same thing happened with the fracture processing. The fracture processing decreases at the same time. Why this is happening? The first thing we can see that the thickness causes some kind of brittleness, or not really brittleness, is the thickness what it causes that the mix behave, or the sample behave as a more brittle sample. That's what we can see from the flexibility index. When we see the fracture processing, here I'm mapping the fracture processing, we see that the fracture processing decreases as the specimen thickness increases. So what is our reasoning of why this is happening? When we increase the thickness, we have a larger specimen. This larger specimen with more material, with more confinement, causes, as I mentioned, more confinement into the development of this crack or the fracture processing, and that confinement restricts the propagation of the crack. That's why we see that when I increase the thickness, all the material, all the strength field were kind of concentrated close to the notch tip at the point of failure. That's what I'm showing here, and that's similar to the behavior of a more brittle mix. So it makes sense to see that the flexibility index decreases due to that, because of this specimen confinement effect that has been also reported in other studies related to fracture testing. The higher specimen induce a more confinement of the material. The second parameter that we evaluated is the case of the air void content. For the air void content, we evaluated from 2% to 10% air void content. And we were able to see, it was very interesting to see that when I increase the air void content, the mix kind of acts less stiff. It's kind of act more compliant. That's what you can see here from the load versus displacement curve. The 10% load versus displacement curve has the lower peak load, so has a decrease in the strength capacity of the material itself. The specimen is getting weaker. And at the same time, the specimen is getting kind of more flexible. It's more compliant from the iFit results. While the 2% has a higher peak load and have a more stiffer and brittle behavior. When we see the iFit parameter, the iFit result, we see the same behavior. When I increase the air void content, the slope that you can see graphically here, the slope decreases. And that decrease in the slope causes an increase in the flexibility index. So why is this happening in the case of the air voice? Previously, we thought that the air voice may cause an opposite behavior. But when we look at from what we saw, and when we see at the result, we see that the air voice kind of cause a more branch structure of the fracture processing. Instead of the material, when I increase the air void content, this air voice kind of makes the crack behavior more branched. There are many other possible reasons of what is happening exactly in the material. We cannot exactly see how that microcracks are connecting. But we saw that the increase in the air void content causes a more branch structure. And we saw from previous parts that a more branch structure indicates kind of a more flexible behavior. While the smaller structure, like one consistent with the notch tip, like here, you will expect a lower fracture processing and a lower flexibility of the mix itself. In the case of the notch length, it was a very interesting case to evaluate the notch length. We saw that when we increase the notch length, basically we have a kind of weaker specimen, a weaker iFit specimen, because we have a decrease in the strength, we have a decrease in the fracture process here, you can see here, we have a decrease in the fracture energy. We have a decrease also in the slope. So we're basically having a specimen who's weaker. One thing that was interesting from this part was that both of them cannot decrease at the same rate, because when we saw the I fit, that is just the ratio between both of them, the I fit cannot stay relative constant regarding which notch length I use for the specimen. And that was something very interesting to see that I was not expecting. So both of them decreases because of decreasing the weakness of the specimen. What is happening with the fracture process on with notch length? When we have the notch length, we saw that the fracture process on decreases when the notch length increases. That's what you can see here in the image in the bottom or in the graph here on the right. The average fracture process on area significantly decreases as an increase in the notch length. And what is this is happening? This is kind of not related to the material itself, of course. What we have here is another effect affecting our fracture processing. During all this presentation, we have been talking about the fracture processing, and the fracture processing is just tensile strengths close to the notch tip of the material, the area that I'm highlighting as red. But in previous studies here conducted with DIC, we already reported that there is a compression zone in the top of the specimen of the eye fit. This compression zone typically stays relatively the same regardless of the notch length. However, the fracture processing area changes its location depending on the notch length. When I increase the notch length, this fracture processing area gets closer to the compression zone that is kind of stay fixed all the time. And here we can see that these compression zones start interacting with with what we call the fracture processing in this study. And because of the fracture processing is tensile opening strengths, and you have compression strengths on the top, this compression strength is kind of restricting the opening of the material. So it's kind of restricting the development of the fracture processing. And that nicely explains why this fracture processing is decreasing when I increase the notch length of the specimen. Finally, we evaluate the loading rate impact, and this just behaves as a normal asphalt mix. We know by asphalt that it's a viscoelastic material, so we should expect that when we increase the loading rate, we have a stiffer behavior of the mix. And when we increase the loading rate, we will have a larger peak load and a more brittle failure, more brittle behavior. So when I increase the loading rate, what I should expect? Higher slope, increasing the fraction energy because the material is getting stiffer, and a drop in the flexibility index. And in the fracture processing area, we saw the same thing. The fracture processing area gets smaller when I increase the loading rate. And why? Because the material is getting stiffer, similar to what happened with the recycled material that I showed before. So there is a decrease in the fracture processing area because of that. Basically, this is just the behavior of asphalt itself. So, as a summary of everything that we presented, the first thing we saw that the thickness all these parameters causes an effect into our fracture processing and the flexibility index. And the fracture processing go hand in hand with the flexibility index. We saw that both of them, the FI and the fracture processing decreases when I increase the thickness. And why is that? Because you have the effect of the specimen confinement when you have a larger specimen, a larger thickness. In the case of the airboys, we increase the airboy content, and what we saw, an increase in the FI and an increase in the fracture processing. And why is that? Because we have a more compliant material, and we have a material that when it's going to fail, is branching out, and that is restricting the development of the crack that is going. So the crack propagates slower. In the case of the notch length, the effect on the FI was minimal. Why? Because we saw that both of the parameters, the slope and the fraction energy, decreased hand in hand. So there was not a significant effect into the FI. However, there was an effect into the fracture process, and it was because of the interaction of the compressive strength and the tensile strength that we call the fracture processing in this study. And finally, the loading rate. In the case of the loading rate, both of the parameters decreased as I increased the loading rate. And why? Because of the behavior of asphalt. The material is getting stiffer, so you would expect a lower FI, and also you should expect a lower fracture processing because it's getting confined into the notch tip. Basically, this is just the same summary as I just mentioned. And with that, I will probably conclude my presentation, and any questions so far from the audience or the YouTube audience are more than welcome.
Yeah. We're going to get 2 quick questions. We'll have to proceed with the second presentation, and then after that, you can have more questions for the presenters.
Okay. I think from your presentation, the DIC still cannot explain why, with the airborne increase, the FI increase, right? Because I think we got a lot of questions in the last 2 TRBs. Why a lot of people are asking why this is happening, and for sure it's not true in the field. So, do you have any explanation on that, or?
So our explanation so far is the branching of it. We didn't saw this before we start applying DIC. We have no idea of why the FI was changing with the airborne content. But what the DIC allow us to see is the branching out of the material. So basically, the fracture process zone controls how the crack propagates. If the crack, you have seen typically when the eye fit is stiff, when the material is stiff, you have a very brittle behavior where the crack propagates straight forward, and that crack propagates fast. When you have a more flexible behavior, the crack propagates more branched. Airboys are causing that the crack propagate in a more branched way. We have seen that with the fracture process zone, and with also we actually seen the specimen that I tested. So when the crack propagate more branched, you will have a slope that is less steep, because that material is propagating slower. And that's what is causing the change in the flexibility index, that branching of the cracking that is making the crack propagate slower. Because we saw the fractional energy changes, but it's not as significant as the change in the pulse peak load, what it caused the change in the eye field.
Yeah, can I just have a follow-up? So you said your airboys introduce longer route, right, for
Yes.
fracture, but like your air, it does not it's not like your like a mix, like a binder or something. Is that the long distance means?
There are many possible ways.
Because we have what we are measuring is the rate. It's not the distance, right?
We are measuring the propagation speed, right? What do you mean with the
we're
slope?
measuring is the speed.
So imagine that you have a crack, and this crack, typically in a brittle failure, goes straight forward. But if you have many airboys and this crack wants to propagate to the airboys, these airboys are going to start branching out the path of the crack. So basically, you don't have a straight crack. You have a crack that is branching and branching, trying to follow wherever are the airboys located. I cannot confirm that with DIC because we cannot see that level of detail with DIC. But we can see from the strain field that something similar to that is happening. This crack, instead of going fast and straight, is going more branching and branching. Maybe the airboys are just causing the change in the path, or something else is happening there. But that's what we just limiting to just mention there is a more branch structure that is causing this behavior.
One more question, and then save the other questions to the end of the presentation.
Yes.
Very nice presentation.
Oh, thank you.
With the increasing thickness, how do you know that what you see at the surface is a good representation of what's happening inside the material, especially with the higher thickness material?
That's a limitation of our technique, of what we have. We just only have what we can have on the surface. I cannot guarantee you that it's an actual representation of everything that is happening inside, because right now we cannot look at what is inside itself. We should just go and try to model the same behavior that we have done in other studies to make sure what the modeling says cannot deflect with the DIC. But we just have a mirror or a deflection with the surface only. But I cannot guarantee, as you mentioned, that inside the material maybe have a different behavior. We just kind of assume that is what we see in the surface translated into the interior of the material.
Okay. Right, thank you, Jose.
No.
Right, our next presenter is Singhiv. I think all of you know who Punit is, and he's a PhD student. And he's going to make a very difficult presentation. He's presenting a work that he was not involved. So let's see how Perez is going to take this challenge, okay? And this place is full of challenges, right? And that's what we throw him at this time to do this presentation. He's going to be talking about total recycled mixes, TRA. This is a really interesting presentation, and let's give him a round of applause.
Thank you, Dr. Ozer. Good afternoon, everyone. So, as Dr. Ozer mentioned, that this is a work which I'm presenting, but it's a work by Fazal, who's our former student, and fortunately, it's his birthday today. So, happy birthday, Fazal, if you're watching. Yeah, and Professor Al-Qadi, Dr. Kamal Hussain, and Dr. Hassan Ozer. I'm just doing the presentation part, but everything is done by them. So, the idea is to characterize the total recycled asphalt mixes and correlate it with its field performance. So the motivation came for these TRA mixes was to utilize the waste materials which were being produced in Chicago area and to accommodate those waste materials in your asphalt concrete production to reduce the cost. And with that idea, the TRA mixes were initially developed at District 1 by IDA. So these mixes followed a special provision and which allowed them to use up to 40% of binder coming from the recycled resources. At the same time, they were allowed to use up to 5% of RAS, and there was no restriction on the amount of RAP, RCA, that is recycled concrete aggregates, or slag to be used in these mixes. So with the first trial, which was done in 2013, the typical mix was an N50 mix design for the surface course with a 9.5 nominal max aggregate size, and 97% of the material was coming from everywhere. Crushed concrete, coarse wrap, fine wrap, steel slag, shingles. And the virgin material which was present was just the binder, which was around 3 to 4%, depending on the design. And this is how the mix design for a TRA mix looks like. So if you look, the asphalt binder content is typically on a higher side, 6.5, which is the total asphalt, not the virgin. The virgin asphalt is around 3%. The air voids were intentionally kept on a lower side, design air voids, to incorporate more liquid into the mixes so that they can compensate the effect of AVR. And the VMA properties were similar for around 15% as it is required for 9.5 nominal max. The TSR values passed, and the Hamburg Rutting tests were way good to have something like this, like 1.7 millimeters. So in all, the mixes were passing the design criteria. This is how a typical TRA mix would look like. You have concrete, slag, wrap. Now, at the time of the first placement in 2013, we had different type payment structures on which these mixes were placed. The first of them was a typical PCC base, PCC payment, on which we had a 1-inch leveling binder followed by a 2-inch thick TRA mix. And the second type of payment structure on which these mixes were applied was a composite section with 3 by 4th of an inch of leveling binder followed by 1.5 inch of the TRA surface course. In this particular study, several mixes which were placed on the field from 2013 to 2015 were evaluated, and except the 2014 mix, which is highlighted here, all the mixes were TRA mixes, and the highlighted section, which was an N7030 mix, was the control section through which these mixes were compared to. If you look at the mix designs here, most of these mixes are on a higher recycled content side, up to 48 to 60% ABR, with recycled concrete aggregates in some of the mixes up to 30%, and steel slag varying from 15 to almost 70% of steel slag as an aggregate source. So, at the time of placement and construction, there were not many problems encountered, not many problems were encountered in volumetrics. However, we need to think about what happened to the performance. So, do you think what would have happened to the performance? Any idea? Any guesses? The TRA mixes.
It performed beautifully.
Beautifully? Okay, let's see. So here's a snapshot of what happened. So these were placed in 2013, and if you look at from 2014 to 17, you see that there is a distress along the center line started right after the year and continued, and the distresses kept on accumulating. This is the other mix which was placed on in 2013, and again you see highly distressed centerline cracks, transverse cracking, all sorts of alligator cracking. Same happened with the third mix. So even though we had a design of using these TRA mixes, there was something which was going wrong, and with that idea, the research objective of this particular study was to characterize these TRA mixes for laboratory performance in terms of fatigue cracking, thermal cracking, and rutting susceptibility. To understand these mix design characteristics in order to improve these high ABR mixes and correlate the lab performance to the early field performance, which we saw that was not good, especially for the 2013 mixes. So we started with sampling of these mixes at the plants, and this is somewhere around 2015, and this is, I think I am standing here, looks pretty young compared to what I am today. This is
involved, right?
Yeah.
I misspoke. You were part of the study.
Yes, so I was part of this study, you can see here, and I think this is Ibrahim and this is Aaron. This is Jim at the back. So we started with sampling of the asphalt material from the plant, brought it to the lab, blended it, splitted it to get the samples to be compacted and get our testing samples. We did several testing on these samples. As part of this study, we'll just talk about a couple of tests which we conducted for the scope of this particular presentation. So IDT was one of the tests which looked into the creep compliance and the master curves of the creep compliance, which gave us the stress relaxation potential of the mixes, followed by the IDT test. The complex modulus test was conducted to determine the stiffness of these mixes, and a variety of test temperatures and frequencies were tested for the plant mixes. In order to incorporate the rutting susceptibility, we did a Hamburg wheel track test, and to investigate the cracking issues, we looked into the IFIT test, which was developed here at ICT, as Jose mentioned. So the typical test matrix for this particular scope, this particular study, was to test lab compacted plant mixes for IDT, Hamburg, IFIT, and E-star. While for the field course, for the field course, we have to exclude the E-star because of the specimen dimensions and the availability of the size we have for the field course. Let's jump on to the test results. So the IDT results from the creep compliance master curves, we obtained the relaxation potential and all the TRA mixes. So 140 is our control mix. Rest all the mixes are TRA, which were placed over 2013 to 2015. And we see that these mixes have a lower relaxation potential compared to the control mix, which is anticipated because of the high recycled content they have. With 137 and 338 being the lowest values, and if you recall from the numbers of the mix design, these two mixes have high amounts of RCA, and the rest of the mixes doesn't have the RCA. RCA is recycled concrete aggregate, which allows more absorption and leaves less binder for the relaxation for the mixes. When we looked into the IDT strength, they were comparable to each other. Not major distinction can be made out of the IDT results. They were pretty comparable to the control, except 138 mix, which had high amount of slag, which was around 68%, which might have made it peak up. But in general, if you look at the lab mixes as well as the field cores, they are pretty much close to each other in terms of IDT strength. When we look into the modulus data, now on the higher frequency side, we are not able to distinguish between the mixes. But when we try to see closely into the lower frequency region, we see some sort of an envelope. However, you cannot distinguish clearly when you are in the middle because these mixes vary within itself a lot, and also it depends on the type of payment structure you are placing these mixes on. So, but one thing is clear, that the total recycles which were placed sometime during 2013, which had recycled concrete aggregates as another source of recycled content, you see that there's an envelope of stiffer mixes, 338 being the stiffest, and your control mix is on the softer side. So you kind of see an envelope within which you have lower curve is the control mix, and the top curve, which is the stiffer one, is the TRA mix, and all other mixes somehow come into this envelope. When we look into the Hamburg wheel track test results, all of them passes the Hamburg wheel track test, which means that they are good with the rutting susceptibility, and it should be because they have a lot of recycled material to it, less available binder, and that's where we see that these mixes generally pass the rutting criteria. However, we cannot see a consistent trend because the mixes are so different from each other that it will be difficult to kind of separate all those mix variability and to answer this effect. But in general, they all pass the rutting test because they are recycled. When we look into the IFIT results, now the Illinois requirement for IFIT is to have a minimum IFIT of 8, which all of these mixes are barely passing, are unable to pass. We'll see here. However, there is a takeaway here is that RCA adversely affects the AC cracking resistance, and probably this is due to the high absorption rate of those RCA aggregates. And you see that these two mixes, 338 and 137, kind of stands out because of the presence of RCA. All of the mixes, they are stiffer, they fall below the 8 threshold, but they are better than if we have RCA in it. So in order to put these things together, we need a mix which can perform both for cracking as well as for rutting. We need to have a balanced mix, and we don't want our mix to be too soft and too brittle. So with the idea of balanced mix design, which we came up with the 128 study, which gave the IFIT, there are different sections in which we can divide our mixes based on the flexibility they possess and the rutting susceptibility they have. So with this idea, we plotted the mixes, all our TRA mixes along with the control mixes on this balanced mix plot, and we saw that the mixes generally fall in the stiff to brittle range because of the presence of recycle. Now within these mixes, the 338 mix stands completely out, and even 137 has a lower FI because of the fact that they have RCA in it, and that's causing it to behave in a much more brittle way compared to the other mixes, which are marginally on the line of IFIT value 8. However, all these TRA mixes are good in Hamburg. Now we had a challenge with this 2D. We have a challenge with the 2D balanced mix design concept, and that's where we moved into 3D balanced mix concept to incorporate those mixes which, even though may pass by Hamburg wheel track test, but are still softer and can pose a challenge in terms of performance. And that's why this idea was introduced with this study to look into the 3D concept. And the 3D concept is just an additional dimension being added to the balanced mix design, which is of secant modulus. So secant modulus is a parameter which we obtain from the IFIT. It's an outcome of an IFIT test, and it is defined as the ratio of the peak load, 50% of the peak load divided by the displacement happened up to that particular load level. And that's how you define the secant modulus. So secant modulus anywhere between 2 to 10 kilonewton per millimeter was assumed to be a safe side for a mixes to be okay. Anywhere lesser than 2 of a secant modulus kind of indicates a softer mix. So all these mixes were kind of in a safe zone. In terms of secant modulus. They were not that soft. However, they all failed IFIT requirements of 8. When we consider the field performance, now we have the data for rutting progression over 3 years, from 2015 to 2017, 2016 and 2017. We saw that the rutting resistance kind of increases as we age the samples, and we saw a decline in the rut depths in the field samples. When we look into the field performance, we see the rut depths slightly increasing, and that's intuitive because as you are passing the loads during these years, you see a trend in increasing rutting because of the moving loads. However, in some of the cases, we saw that in the third year there was a slight dip in the field Rutting values, which may be attributed to where these samples were, where these measurements were taken. So it can be because of that. But in general, we saw that the Rutting values for the field sample, for the lab compacted samples, for the field cores were lesser, were decreasing, and the field values were kind of increasing. When we look into the field cracking of the mixture, the field cores, we see that with aging, we saw there was a trend of declining Fi as expected because the mixes are becoming brittle and brittle. In some of the cases, like in third year, we saw there was a slight increase, but in general there was a decreasing trend, and which was also evident from the cracking data, which showed that the transverse cracking was kind of increasing as you age the samples. If you see here, the mixes which, like 185 mixes which were placed around 2015 were somehow performing better. The reason can be attributed to there was no RCA was being added to these mixes, because in the 2013 mixes we saw that the RCA was kind of causing a problem with the cracking susceptibility, and so that was kind of eliminated from the 2015 mixes, and that's why they are performing a little better than the 2013 mixes so far. If you look into the cracking and the flexibility index correlation, field cracking and flexibility index correlation, it shows a decent trend in terms of correlation. So what we get out of this study was that the control section and 2015 mixes were kind of having a better cracking performance compared to the 2013 sections, and which can be attributed to several reasons, which we'll talk about. So first of all, TRA mixes are relatively less compliant because of the presence of high recycled content in it. Second, adjusting the grade of the binder and binder content does play a role in kind of lowering the modulus and making it behave much more flexible. Using a stiff and a brittle TRA mixes over thin overlays on jointed concrete resulted in premature cracking. So we saw that the type of pavement structure used, there were two different kinds, and depending on what kind of structure you use a thicker lift or a thinner lift of TRA, total recycled mixes, and which can also contribute to the cracking performance. And high ABR mixes can be engineered if we can use the balanced mix design approach, which can tell us whether this mix can suffer from premature cracking or rutting issues. And with that, I would like to acknowledge IDOT and students at ICT and the research engineers David Lippert, Joe Vespa, Shenghua, who are involved in the project. Jim Meister, you saw it in the picture, and I think I was there too in the picture collecting samples. So yeah, thank you for your patience. And
I have two questions,
Yes.
like general question. You go back to the chart that you were showing. What were the tests that were made?
oh,
Yeah.
yes.
Yes, this one. So here, whenever we're looking at IFIT, we're doing a fracture test, right?
Yes.
When we're doing Hamburg, we're looking at the rutting.
Rutting.
So the dynamic models that we're looking at, what are we trying to target there? Is it fatigue?
So for dynamic modulus, we are trying to address the overall stiffness of the mix,
I mean, you're
not the fatigue. For fatigue, we have beam fatigue we conducted as part of this study, but here we are primarily looking into the thermal cracking and overall cracking using IFIT.
I'm asking this question because you're comparing, like, this is more of a fundamental test
Yes.
compared to some performance test. But the E star has a direct correlation with the fatigue performance. So I was wondering why, whenever the people that work on this project, whenever they were comparing the master curves, why didn't they look at like 20 degrees Celsius and then they compared the numbers there? Because I think when I looked at the curves, all of the curves, and then they are like crossing each other, I didn't get anything out of this. But maybe if we look at where the fatigue is the most prominent, which is like a certain frequency, maybe like 10 hertz.
I believe I believe that all these master curves are plotted for reference temperature 21 degrees Celsius.
But he's talking about just plot bar chart showing, let's
Yeah.
say, 20 degrees Celsius, 1 hertz or 10 hertz.
Yeah, I
or
think
minus,
because
right?
it has a direct relation with fatigue, so it can be a good indicator if fatigue is not performed.
Yeah,
I mean, usually it's not in this project in particular, but in all of the project, it's nice to see, like, usually we think, okay, I'm drawing the master curve, I see that it's like higher or
Yes.
shifting.
Yes.
But usually we're not seeing that, we're seeing like they are overlapping or something. So maybe we should find a better way of representing this data, because this is a very important thing. And my other question was for the course that you take from the field and you test. So usually, like, even if at the beginning of the construction you take cores and then you test them before they age,
Yes.
you'll see that you'll have a variation. I mean, the compaction might not be the same, the material, the aggregate interlock, the aggregate. So how do you account, like, we usually, whenever we're looking at year 1, year 2, year 3, it's, how do we compare them if they are not from the start the same?
So it depends on what test you're talking about here. All the tests, when you say
No, I mean, let's suppose IFIT. But
Like for
it can
IFIT
be applied to anything.
Yeah, so for IFIT, what we try to do is first of all, we try to apply the correction factors. Correction factors like air void correction factor. Because over the time you will see there's a compaction happening, and the field cores which were extracted sometime, let's say during 2017 compared to that of 2015, will have a lower air void. So we try to use the correction factors which were developed for IFIT.
Maybe I didn't explain myself well. So whenever you're taking cores,
Yes.
I mean, at the beginning, before there is aging. So now here what you're showing is year 1, year 2, year 3.
Yes.
So you're going at year 1 taking a core, second year taking another core, third year
Yes.
taking. But maybe these 3 cores that you're taking
They're
from
not-
the beginning, they are not the same. I mean, maybe one has been more compacted. So how do you think in general we can account for that? Maybe do more testing along a certain length?
I think the best way, if I'm not wrong, just correct me, Dr. Rosette. So I think if you take your samples, make sure that you take it from that similar kind of area. There will be differences. Like, for example, if I collected my cores from one region for over the years, let's say for 3 years, I need to make sure that I'm collecting from the similar patch. Because if I move from one patch to another, there can be differences. So you're right, like there will be inherent variability. If I take one core compared to the other core, that's what you're saying, right?
Yes.
Yeah, so there will be a variability. So we try to assume that when we are compacting, let's say in an area of, let's say, 2 meter or 3 meter range, the mixes will be pretty much the same compared to if I go, 100 meters off that particular location for the second layer and collect the cores. So yeah, it's very important that you collect the cores from the previously collected site very close to it, so that you can avoid that kind of differences. There can be other ways which you can probably ensure that by image analysis, something like that, where you can see that the structure is kind of similar to what you had before, and then you can take a call whether you need to consider this as a valid sample or not. Yeah.
Thank you so
But
much.
if I'm not sure, Dr. Ozar, if you have any other suggestion on that.
It's a challenge for
Yeah.
everything. I think field campaign. I think the more replicate, the better it is. But I think there are certain, like if you go to this cores are sometimes used also for quality control or forensic investigation. It's not only just you should not really just target one area, because if you're basically representing the entire construction, right? If you just get your cores from a very limited area, that may not also represent the entire. If your objective is to characterize the performance of that mix, that section, right? You may not just focus on just one small batch. Maybe that batch is one replicate, but you move to another batch, maybe 100 feet from that location, get another sample 100 from that. That can represent that overall, let's say, use of that mix and production of that mix.
Maybe staged replication can be an option. Like staged replication, like more samples. Let's say you have 3 or 4 at least samples from one section, and then you compare the same sample, like set of 4 or 5 cores 100 meters down the line, so that you can compare within also, and
But there's one thing that you can look at. Of course, one criteria that you can check is the density. The density, they are constructed for a certain target density. If the density H is achieved, then you may at least feel a little bit more comfortable. Of course, things can still vary, but the density is the only criteria that you can look at. It is density and thickness, right? When you test
But
it.
if we look at like if we take one wheel path and then the next time we take the other wheel path, shouldn't they be similar? Since they are exposed to the same traffic, and then when they were constructed with the same machine that was going over both at the same
So yeah,
time.
for that location, you can probably target taking the course close, right? But you need more of those replicas to represent that entire project. But for that location, you try to stay within that area.
Yeah.
But there is also concern that you cannot take too many courses from the same area. You
Otherwise
start,
you have
start damaging damaging the pavement.
And yeah.
Yeah, just a follow-up comment to Isaac's question. I think if you're not sure if this area is homogeneous for a core drilling, I mean GPR can definitely do the help, right?
Yeah,
I mean, if you're not sure if it's the same area in 10 years, you can like run this continuous test like several times a year or whatever frequencies you want, and make sure that this particular area of the patch, they are the same right after the construction, and you can keep taking course from this particular patch over the years.
But yeah, the same challenge, like you cannot have more cores because if you take out more material, you need to put in something.
Yeah, but I mean, you can run the test like infinitely over the same
Yeah.
period of area, right?
Thank you for your question. Any more questions? I think this is like general question.
I
Yeah.
have a question, but my questions are for Jose.
Yeah, sure. I mean that's
Yeah, it's a lot.
Yeah. Jose.
Come to the podium, Jose.
Yeah.
So the FPC fracture processor,
Yes.
did you assess any way how much of it is aggregates and how much of it is binder?
No, by quantic, we don't have like the percentage, but most of the time, I would assume that we are talking about 95%. I would be very confident to see 95% that is binder and the mastic itself. Like we typically, because this thing of evaluating that part, what we basically did was the following. When you do DIC, you paint the specimen. So what we do is just we take a picture of the specimen before the painting, and we put some control points. So when we have the painting, we can correlate that strain field over the picture before the painting, and that's the picture that I show in all my slides that I have the setup, and you have seen the aggregate. That's how we evaluate that most of the fracture processing, and I'm very confident it will be more than 90% is binder. I mean, this is mostly mastic what is failing. There was some small instances, some once in a while instances where you have an aggregate that is already fractured before that, and we were able to see the crack where the fracture processing went to the aggregate. But most of the time you will see that, and we are pretty confident that the fracture processing is in the mastic itself.
For this temperature,
For the temperature that we're dealing right now. This is for intermediate temperature 25C, what we saw today.
But remember also we are dealing with very soft aggregates. You were looking at the samples, right? When we
I asked
were
you.
preparing for there were some.
Yeah.
If you look at the broken specimen, you will see some broken aggregates.
Many.
Normally you wouldn't expect this at this temperature in a fracture test, but because we are dealing with limestone, very soft aggregate, they can be broken too, but not really to the extent that they can be. Then they should be at lower temperatures.
Yes.
I have a question for Jose.
Yeah. So about the
Go ahead.
So yeah.
Chairman.
about the air void correction equation, what is the appropriate? Because I think the paper you published is the appropriate air void range is different than what Maxwell come up with. So I don't know which one we should follow.
Right now, we recommend over than 8% air void content. We should try to avoid that
I
from
mean,
there.
lower side.
From the lower side, we haven't put like a minimum range in that case.
Yeah, but Puneet, you remember that we think that lower side has a very big issue, right? We saw some field course like 1%, 2%.
Yeah.
And
I mean
correcting
there's
is
also
like
one
50.
138 mix I think is 0.4%, 0.5%, and that's what causes air voids to shoot, like Fi to go.
Very
Yeah.
So
It should be a range.
yeah, I think Max in his thesis he mentioned like I cannot remember it correctly 5 or 3, mostly like 5. So but like field course we have a lot of field courses that's below 5 and I think people from other institutions they kind of have these issues when implementing IFIT on the field course. So I think if it's possible to come up with something for extreme lower airports, of course that'll be much faster.
Is Utman here?
But
No, he's here, but he's not here.
Yeah, maybe the rate adjustment can also
Address that.
address for such high stuff, mixed with high stiffness.
I am okay.
You have a question?
See,
So I have a quick question regarding the DIC technique. So I saw the pictures where you highlighted these fracture or cracking areas. So how do you like find out these areas? You do that manually or automatically?
with MATLAB, basically we take from the DIC, what you get is the whole matrix of the
Picture.
each point of the image and the strain that you are measuring at each point that we call subset. It's not exactly a pixel, it's just a collection of 20 by 20 pixels in one point. And we have basically the location of each of them. And we are basically taking that locations, plotting them, and selecting the strains that are higher than 3000 as the locations where we have the fracture processor.
So you have like a preset threshold for this pixel.
Yes, we have that code for that one.
Thank you.
I have a quick question. And when you were explaining how it cracks and you were talking about the fracture process on.
Mhm.
So, does the crack happen on the edge or in the middle? Because this is
That's something that will I cannot make one conclusion out of here. Like first I didn't look at how much, but I have seen that happen in both cases.
But the thing is, I'm asking this for a specific reason, and I think maybe we can do it. That you're using the IC check it if we take a picture not of the cracking from this side, but maybe from the bottom.
Mhm.
You can put like a camera or something and check along the width of the notch how it's happening. And my main concern regarding it is not plant mixes, but more whenever we're testing something from a core from the field. Because usually any test that we do and then we take a core and then we cut it, and the way that we place it might not reflect actually the problem that we're facing. Because let's suppose we have aging and then we have thermal cracking. Most probably it will happen, go like from the top and go to the bottom or something if it's like more stiff or. So maybe the way that we're testing, not just IFIT, but maybe like IDT or any other test, might not reflect where the crack will initiate in the field.
Mm-hmm.
So maybe we need to check if it's starting from this edge that we're checking or it's from the middle, and maybe this will lead us to create a new test for the specimens that comes from the field to target the weak areas or the location where the crack will happen in the field, as compared to synthetically select the location.
Yes, that would be something a little bit different because here we have some limitation of where we are observing the test itself and also what we are looking in the.
But if you think if we take the picture from like the bottom
Mhm.
of it, so this is the support and this is the specimen, and then we put the camera this way, can't we check what's happening along the crack?
We can look at what is happening along the crack lane, where is that strain initiated. That's
Yeah,
something that
No,
can be
how
done.
do you do that?
What we need to come up with,
Huh?
Light.
what we need to get is our different testing equipment. Because right now our camera doesn't
No.
fit.
Even let's say, suppose that you put it underneath. What are you gonna see in there? I mean, there is the notch.
It's
notch
just a
is
small
only-
area you
notch
can
is
see.
only 1.5 millimeters. Let's say
1.5.
wide, right? 1.5. So what you cannot really shoot.
I'm worried
get
about the
pictures
light
between,
issues.
and then you can maybe get.
But we
whatever
don't
is
have
in the
light.
crack, huh?
You so
Let's
in
see
order
if
to
you have
get-
even the light, but you have only
Point.
an opening of 1.5 millimeters
Yes.
that you can reach to the crack tip from the bottom. If you look at it from the bottom,
Yes.
right? Only 1.5 millimeters, so you cannot really access the crack from the bottom. Right?
Even more than that, the problem with
Yeah.
that opening is that it's typically rounded. And in DIC, you need to have a flat surface. The algorithm assumes that you have a flat surface. So if it's flat, you may have, the only thing that you can if we have at least one flat, you can at least compare if along the length with the small area that we have were initiated. It's a very limited. But my main concern is not really what Professor says is that it's rounded, and in rounded, you will not, DIC will not work for our DIC application. You will need to have a higher like 3D DIC to try to evaluate that algorithm. Okay.
All right, any other questions? One more, the last one.
Jose, I think regarding Singhi's comment, I think your fracture process zone can be interpreted as an area of dissipation of energy.
Mm-hmm.
Then, because the fracture process zone is bigger or larger, we're dissipating more energy, and that could explain the more ductile behavior.
That's one thing, and remember the strain magnitude. Here we're just looking at the size, but the strain magnitude is something where we need to look at, because the strain magnitude between a smaller fracture process zone and a larger process zone differs. You don't have, that's something that was limited here, and I will be a little bit careful when we just assume that the area is directly related to the energy. It's not only the area, it's how much actually strains we have there. So this is another thing that was not included in the study.
Okay, well, let's thank the presenters.
He had a question for you.
Meet and greet with the presenters follows.
Yes, no, I see that. We have so many questions.
I had a question.
Famous Jose.
No, the people here made it a group meeting.
If we have like lunch